series. Let's see. Okay, that means let's see what it is. A power series is a series in which each term is a power function. Yes, and we know what is power function, like let's say x to the power of 1, x to the power of 2, 3, 4, and so on. That means we will have, okay, we will have this type of formula. I will switch the video. And then this is sigma notation, which is of course the summation, the power series, and we have coefficients c sub n, and then we have x to the power of n. And n is changing from 0 to infinity. C sub 0 and x to the power of 0, of course, is just 1. And then c sub 1, x to the power of 1, c sub 2, x to the power of 2, and so on. That we can see. The expansion looks like a power function. Okay? And we will call, of course, x, the variable, independent variable, and c sub n is just the coefficient, is the constant. And this will be given. This will be like provided. C sub n will be an exact formula, exact, like let's say 1 over n, or maybe negative 1 over n squared. Yeah? The c sub n will be like defined in terms of n. Okay, and then we have to like still having this sum of infinitely many terms, we have to still deal with convergence and divergence. Okay, we will still use some test, and probably we will use the test that we just learned. Okay, all of the tests which we covered before the midterm too. Okay, let me switch the slide. That means one more time, the power series may converge for some values of x, and may diverge for another values of x. Okay? That means now what we can do. Previously we had the infinite series, which we used the test, we applied the test, but then the infinite series was divergent or convergent. But now, since we can pick the values of x, because x could be theoretically any number, then for some values of x, we will have convergence. For the other values, we will have divergence. That means if we're looking for convergence, we have to find the set of x that is giving me a finite sum, convergence. And now the sum of the series we can call a function, okay? A polynomial function with infinitely many terms. But we can only call this function, yes, if we know, and we will call an interval of convergence, which means the set of numbers that is giving me convergence, set of x. Okay? That means we can say this is power function. The sum of the series is a function, power function, whose domain is the set of x with which the series is convergent with. Okay, that means you can probably guess the main exercise, the main question will be find an interval of convergence. Okay, we will call an interval of convergence, which is the set of x that is giving me convergence. Okay, let's keep working. Okay, let's start with the nice and easy one. Like, let's say that I will replace c sub n with 1. That means the entire, just 1. C sub n is 1. Could be anything, but I choose 1 for all of the values of n. Then the power series looks like that. Just 1 times x to the power of n. And if I will make the expansion, x to the power of 0, which is 1, x squared, x cubed, x to the power of 4, and so on. Okay? And we can realize that this looks like a geometric series because we do have a common ratio between each term. X divided by 1 is x, x squared divided by x is x. That means I do have my common ratio. I can even say the common ratio is x. And we remember that in the geometric series was convergent if the common ratio was between -1 and 1. Now I can replace common ratio r with x. That means this power series converges only if x is between -1 and 1. And as I mentioned the new terminology, an interval of convergence, which we will call just I, okay? It's gonna be set of numbers between -1 and 1. This is an interval of convergence, okay? Which just means the set of numbers. Okay, that's the first one, just x to the power of n. Okay, and of course this is x values. And if the x are outside this interval, we have divergence. Okay. Okay, now let's look at the more general formula. That means we still have a summation, of course, the power series. We have power x to the power of n. We have c sub n, which is the coefficient. But now we have this form like x to the power of n, but we subtracting a number from x minus a. Okay? Because we will see later, this is quite helpful, and we like with respect to an interval interval of convergence. Okay, that's we have c sub n x minus a to the power of n, which that's the expansion. And it's still like x to the power of 1, x to the power of 2, and x to the power of 3, and so on. But we have this minus 1. And we will call that if you see this form, if some number is subtracted from x, like number a, we will call that this is power series centered at a. Okay, or we can say a power series in x minus a, power series about a, but I think all of them are equivalent statements, but I think this one is nice and kind of like exact description, and you will see in a minute why. That's mean if you see something like that, we can say is centered at a. Let me come back for 1 second to this slide. And can you tell me, looking at this formula, what is the center? Because the a value, okay, one more time to this one, this will be a center, okay, like a center of something. We will define it in a minute. That means this is just a center. That means, let's look at this formula. Can you tell me what is the a value? What is the center? Yes, Angela, thank you, Anton, is 0. That's my point. That means a is a 0, which I can say that my geometric power series in this case is centered at 0. And can you tell me what's the middle, like what's the center of this interval? It's of course 0, right? Yes, yes. That means always, that's the reason that is helpful. If we will be looking for an interval of convergence, set of x that giving me convergence, and we will find an interval, and always the middle, the center of this interval will be that value a. Okay, let me come back to this one. Always this number. That means even looking at the formula before computing anything, you will see and you will know the center right away. And that means it's quite helpful. A is quite helpful number. Okay, that means this is of course 0. I can draw it 0, and then we have -1 and 1. That's I can maybe use some weird notation. That means an interval of convergence is between -1 and 1, not including -1 and 1, and the center of course is 0. Yes, which we knew right away. Okay, we do have question. Has to be on the horizontal. Yes, because we're looking, it's kind of like, oh no, because we only have x, right? We only have a set of x. We don't really have y. I mean, we will still talk about the output, the function. Okay, I'm just answering Angela's question. If everybody can see the chat box, that's we're always looking like at it's just 1D, like a set of numbers. Set of independent variables. It's like finding the domain. Yeah, like if we have a function, like let's say I can give you a function x1 over x minus 2. Okay, that's me. Can you tell me the domain of this function? Can I accept any numbers instead of x? Yeah, this is just basic algebra question. Or can you answer this? What is the domain of this function? Probably you know the answer. You can see we can accept any numbers. Yeah, this is just not 2. Thank you, Anthony. I was looking just for this. Yeah, this answer. That means any numbers, but not 2. Okay. Okay, thank you. Yeah, I know. It's, yeah, we don't have all of the symbols on the keyboard, but yes. And then I can, of course, use an interval notation. I can say from negative infinity to 2, from 2 to infinity. But I can also say this. That means we can see we all just looking at the x value, like just, yeah. If you would like to say, Angela, like horizontal line, it's okay. It's, yeah, but we're just looking for the x values. Okay, let's see, let's work on these intervals of convergence. Okay, that's when we did learn one thing. This number will be a center, and we call like a power series centered at A, because that's the middle of my interval of convergence. Okay, that's me. Let's keep working, but before we start, I just want to, like, because what we have, let me come back, we do have like term x minus a. Yes, we can see this. And if you can probably realize here, x minus a to the power of 0, of course, is 1, any number to the power of 0. And on my next slide, I just said that even if x is a, which will be a minus a, okay, we will also say that it's theoretically it's like 0 to the 0, but we're assuming that this is 1. Okay, in this case, because it's just exact values, it's just 0. That means, yeah, it's just a number. That means we will assume for this, in this topic, we will assume that this is 1. Okay, and okay, and then we have also the second note. Okay, if x is a, because that's another important information. If x is a, which means if x has the value of the center of that interval, that a value, all terms are 0. So the power series in our equation above always converges. Okay, that means I can maybe copy this. This is my power series, c sub n, x minus a to the power of n, not to the power of 0. Starting from 0 to infinity. That's we have c sub 0 and then c sub 1, x minus a to the power of 1, c sub 2, x minus a to the power of 2, and so on. Okay, that's when we can see if x is a, because x could have any numbers, and I mean any values. If x is a, then this is 0, this is 0, like all of the terms are zeros. The only value that will stay is actually the first term, c sub 0, which means the sum is defined as a finite number, then always convergence. But please remember, if x is a center, we always have convergence. Okay, I will test you in a few minutes if you remember this. Okay, that's me now. Let's work. For what values of x is the given series, power series, convergent? Okay? I'm still not using a name interval of convergence, but that's what we're looking for. Okay, that's mean how can we approach this? How can we find out? Because what we will have, we will always have a mixture of few formulas. Since this is power series, we will always have a power function inside. And C sub n, right? C sub n is defined as a n factorial. That means it's like another expression. Okay? And hopefully you remember from like before that if we have a mixture of different types of expressions, different types of function, the ratio test was the best test to test something. That we will still use our old test and we will pick a ratio test. That means let's use the ratio test and let's see what we can get. That means what is the ratio test? How do you remember ratio test? Did I type this? Oh no, okay, I typed the solution that I will write for you. Okay, limit as n goes to the infinity, a sub n plus 1 over a sub n. And what we're looking for? We're looking for a number less than 1 for convergence, greater than 1 is divergence. That means we would like to have our answer less than 1, not equal to 1, That's inconclusive. Okay, that means a sub n is n factorial x to the n. The next term will be simply n plus 1 factorial x to the power of n plus 1. Okay, let's see. Limit as n goes to the infinity. N plus 1 factorial x to the power of n plus 1 over n factorial x to the power of n. Okay, let's keep working. N plus 1 factorial I can rewrite as n factorial n plus 1 x to the power of n x to the power of 1. N factorial x to the power of n. Let's simplify factorials, power function, and what we have, limit as n goes to the infinity, and we do have n plus 1 times up. I mean, we have n plus 1 times x, everything absolute value. But what I will always do, I will, at the end, I will kind of like write them separately, because the limit is defining n. That means only n. I can only look at the n expression to evaluate the limit. Everything what is not n, which in this case is x, is simply like a constant with respect to this limit. That means I have to just keep this, okay? Because limit of the constant is a constant. Okay, that's what do you think? What is this limit? Limit at infinity of n plus 1. Oh? It's simply yes, right? Because it's infinity, that means it's simply infinity. And infinity, big number times x. X could be any number, 1, 2, 3, 4, 5. That means infinity times another, like any number, always will give me infinity. Okay, that means this looks like I've never have convergence, because this is definitely infinity greater than 1 based on the ratio test. That means this is never, this power series is never convergent. But do you think we have at least one number that is one value of x that is giving me convergence? It is 0, right? Because actually I should ask you at the beginning, looking at the formula, can you tell me the center? This is the power series centered at what number? Can you look at this? Of course it's 0. Thank you everyone for, because we can see I'm not subtracting n like any number, it's just x to the power of n, not x minus like 1, 2, 3, 4, x minus 0 theoretically. That means this is 0. Okay, that means, oh no, this, we only looking at x. N factorial, it's my coefficient. This is c sub n. Okay, I can write this c sub n, x minus a to the power of n. This will be the general formula for the power series centered at a. That means c sub n will be defined in terms of n. In this case, in our case, we have n factorial, and then x minus 0 to the power of n in our case. Okay, that means this is just not part of the power form. It's just the coefficient. Okay, that means we can see a is 0. That means what we can do in this case, by the ratio test, one more time, we got divergence, but I can say that this power series is convergent at 0 only. Okay, that means I can answer, and actually I can say that interval of convergence is simply a one number, 0. Okay, that's interval of convergence. It's only 0. That means if x, I can answer this, if x is 0, the power series is convergent. Okay, or using my I, interval of convergence, just one number, 0. Okay, even if I've got infinity. Okay, that means this is one case. Let's look at the other one. Okay, and we can see we've got infinity, but we do have convergence at a. Okay, let's take another one and let's look at this one. For what values of x does the power series, the series converge? The same thing. Now I see x minus 3 to the power of n over n. Can you tell me what is the A? What's the center? Yes, now it's free. Okay, that means maybe we can get an interval finally. Okay, good. That means you can recognize center. Good. Can I ask you one more time? If this will be x plus 3, what will be the center? Okay, that means you're good. Okay, this will be negative 3 because we're subtracting A. If it's addition, we did subtract negative number. Okay, but let's come back to the original. In the last slide, 0, infinity isn't indeterminate form. Oh, Angela, I don't know if I understand you. 0 times infinity. Oh, no. We just, okay, it is, but at this point, we don't really have like 0 as a function and infinity. It's just, this is just because n is not like x. That's mean I write infinity, but this is like the exact values. Like let's say 1000, 1001, 1002, 1003, like the discrete, like all of the just the positive integers. Yeah, that means infinity always means like all of the numbers. Now we have just, that we know this will be, in this case, if we will have n times 0, it's simply 0. Right? Even if n is like huge number, because I shouldn't maybe even write infinity, because n means 1, 2, 3, 4, 5, 6, 7, and times 0, each of these numbers will give me 0. Okay, that means it's just like exact values. Okay, I know it's a good question, but okay, that means let's do the same thing. Let's do the ratio test. Ratio test. Limit as n goes to the infinity, I can maybe do right away x minus 3 to the power of n plus 1 over n plus 1, and then times, and I will dividing by fraction means multiplying by the reciprocal, an absolute value. Of course, I am using a sub n plus 1 over a sub n. That's my ratio test. Okay, let's simplify. We have x minus 3 to the power of n, x minus 3 to the power of 1, n plus 1, x minus 3 to the power of n. Am I right? Okay, and the only thing that I can cancel out is this and this. Now, let's rewrite a little bit. I will put n over n plus 1, and I don't have to keep absolute value for n, and I have x minus 3. Okay, makes sense. I have n over n plus 1, that's the part for the limit, and x minus 3, it's still there, but it's kind of like a constant. Okay, now who can tell me what is this limit? N over n plus 1 at infinity. Oh, if we have the same degree, yes, it's simply 1. That means 1 times x minus 3, absolute value, is just x minus 3. Okay. Okay, that's what I have. Now I've got my answer actually in terms of x. And I know, based on the ratio test, that if I want convergence, I want my answer to be less than 1. Okay, that means x minus 3, absolute value of it, must be less than 1. Okay, and now I have nice absolute value inequality. I have to solve this inequality. Absolute value of x minus 3 is less than 1. Let's rewrite without the absolute value. This means that the number inside must be between -1 and 1. And I can add 3 to both sides, 4 and 2. Okay, I think I have my interval of convergence. All of the numbers, I think we say it equals to from 2 to 4. And do you think my value A, my center, my 3 is a center of this interval? Yes, can you? Of course it is. Yeah, I can maybe write on this side, this is x from 2 to 4, and that's my center. Okay, but one thing is missing. I will tell you. Actually, this is my interval. All of the values between 2 and 4 will give me the answer less than 1, and if it's less than 1, the power series is convergent. Okay, but what is important also, the ratio test is not really testing an endpoints. That means 2 and 4. Because let's see, if I will take 2, let's substitute 2 instead of x. 2 minus 3, it's -1. Absolute value of -1 is 1. Do we like the answer 1 for the ratio test? Yes, no, no, of course, thank you, Anthony. Of course, we don't like answer 1 because this means that the test is inconclusive. That means the same thing will happen if I will put 4. Yes, inconclusive, thank you, Angela. 4 minus 3, 1, okay, that we can see 2 and 4, the endpoints, and this will be always the case. I can't test the endpoints using the ratio test. That's what I have to do. I have to do substituting. I mean, let's see how we can test endpoints. I'm taking x equals to 2 and simply substituting instead of x to the original formula. My power series was from 1 to infinity, n x minus 3 to the power of n, and I want x to be 2. Okay, let's simplify. We will have -1 to the n over n. That's me now actually in substituting an exact number for x, I am eliminating my power series. I simply have my infinite series. And what do you think? Do you remember the stuff before the midterm 2? This is -1 to the n over n. Do you think this infinite series is alternating harmonic? Thank you. And it is convergent, right? That means now we can see we will use just the old stuff. It's alternating one, or based on AST, the alternating series test, we can prove that it's convergent. That means this one is convergent, which means 2, I can add 2. 2 will be a closed interval. 2, the value 2 is giving me convergence. And let's do the same for 4. X equals to 4. What we have? 1 minus 3 to the power of n. And now I am substituting. I'm just trying to change colors for you. Nicely see. Okay, I have 1 to the power of n. And 1 to the power of any number is always 1. Okay, I'm getting 1 over n. This one is simply harmonic, okay, which we know that is divergent. That means this one is divergent, and this means that I will not include 4. Okay? That means, of course, we can see the center, we can see the interval, but please remember about the endpoints. I will put nicely. 2 is fine, 4 is not. That means it's an open interval from the right-hand side, but it's closed on the left-hand side at 2. Okay? That means this is nice, typical example. That we do have an interval of convergence, we have a center, and we also have one more thing, one more terminology. We also, as soon as we have center and an interval, we also looking for something like a distance from the center to the edge of the intervals, to the end of the intervals. That means, what do you think? What is this distance? This is center, and then from the center, each direction, how many units we have to go to reach? It's 1. And we call a radius of convergence. Radius is 1. Okay, that's just the terminology. Interval of convergence, radius of convergence. Radius is just the distance. It's like a radius, actually. We don't really have the whole circle. We're just going to the left and right, but it's like a radius, like a distance from the center to the edge, to the end of the interval. Okay, good. And we do have a solution here. If you can pause the video and you can look at this. Oh, and I have one more function. Shall we do it? Let's do it. And this will be the last example. I know looks quite complicated, and this is also a power series, because we can see x to the power of 2n and lots of different formulas, which this is of course c sub n. We do have the name for this. We call like a Bessel function, but we shouldn't be worried for the names. It's just the power series. And since I'm naming this as a function, I can only name this as a function if I will find the domain, which means an interval of convergence. Okay? That's mean finding domain means the set of x that is giving me convergence. Okay, let's try really fast to apply the ratio test. Okay, for the first time, and I believe for the last time today. That's the ratio test. Okay, what I have? Okay, I have -1 to the n, but absolute value will, this is still there, of course, but absolute value will eliminate -1 to the n. That means I shouldn't be worried for this one. But I will have x to the power of 2n plus 1 distributing 2, I have plus 2. 2 to the power of 2n plus 1, but distributing 2 is this. And n plus 1 factorial and everything squared. Okay, and then I will divide by the reciprocal, I mean multiply by the reciprocal. N factorial and then x to the power of 2n. Okay, let's see if we can simplify, because this one, x to the power of 2n, x squared, 2 to the power of 2n, and then n factorial, I can maybe do this way. 2 to the power of 2n, 2 to the power of 2. N plus 1 factorial, I mean n factorial times n plus 1, and then n factorial n plus 1, because it's squared. And then 2 to the n, x to the 2n. And you can probably see this is gone, this is gone, this gone, and this is gone. And let's see what's left. Limit as n goes to the infinity, and I have to collect all of the n's. 1, n plus 1, n plus 1, and then only x squared stays, which I don't even, oh, I'm missing something, 2 to the power of 2, 4, which is important, maybe not in this case, because we will get the same limit with 4 or without 4, but still we have to have everything. Okay, that means, can you tell me what is this limit? Limit at infinity of that form? Like 1 over big numbers, of course, 0. And now 0 times anything, again, in this case, don't worry, this will be simply 0. And 0 is always less than 1, which means domain of this function, or the interval of convergence, are all of the numbers. I can say domain are all of the real numbers, or using a new terminology, all of the real numbers. Interval of convergence is all of the real numbers. Okay, that's like the third case. The first one was just zero, just a center. The second was like a typical interval, and this one is all of the numbers. But let's check one thing. Again, I'm going to ask for the center. Looking at the formula, can you tell me what is the center? Can you find the x and check if I'm subtracting something from x? Of course, it's 0, because it's just x. Of course, it's to the power of 2n. It's complicated, but that's different thing. But x is just x. That means a, the center, is 0. And do you think that makes sense? If I have an interval of convergence, all of the numbers, can I say 0 is the center? My number line? Yeah, like this is 0. And like we have the interval of, an interval of convergence are all of the numbers. That means I can say that 0 is a center. And now, what will be the radius of convergence? Radius. This is all real numbers. That's different. because you remember what is the, it's simply infinity, right? Really good. Yes, I know it looks weird, but that's actually how we will define, because the distance is simply infinity. I know we kind of playing with this infinity, but the distance like from the center to the edge is infinity. Yeah, in this case is infinity. Okay. Yes, distance is always absolute value, right? That means radius is always like positive. Yes, correct. Okay, that's now I think I have the summary. Yeah, this is my notation, my solution, and we don't have to look at the function for now. Okay. You can probably, I will provide the slides, you can read, but I think I said everything. You know the radius of convergence. I'm just describing all of the cases that we did. Okay, that means this is maybe the nice like a picture of the number line. That's mean what we may have. We may have this center, and we can see the radius. Yes, if we have the center, we're going R units to the right and R units to the left. And we will call the pink line as an interval of convergence. Okay, in this case, that we may have. And of course, we have to always check the endpoints. That's because you can see on this interval, we may have open, open, or maybe closed and closed, open, closed, open, closed. And we know how to check them. And I'm just looking for this. That means this is the summary. And let's just double check. We did example number 1. The radius of convergence was 0, and the interval was just one number, 0, the center. The second one, that was an interval of convergence, and that's the radius. And for the last one, all of the numbers are the interval of convergence, and radius was infinity. That we can see we have 3 different cases. Okay, that's we make sure that we we understand this. Okay, that's just looking at this. And I think, okay, that means this is the geometric one, which we can always, we do have an interval from -1 to 1, and radius is 1, of course, distance from 0 to 1. Okay, that means that's everything for 11.8, but let's let's do not finish. I will still talk a little bit about 11.9. Okay, let's see. I have a few examples, but you can check my solution. It's the same thing. I have another one. The only thing, okay, can you tell me the center? What will be the center of an interval of convergence? 0, thank you, really good. That means 0, we don't know what it is. You can, and please apply, if you would like to try this, apply the ratio test, and you have the solution. What about this one? What is the center for this one? Oh. Anthony, Angela, no. We have to be really careful. Yes, Samuel, Anthony, thank you. Because we subtracting, okay? That means the center is gonna be -2. Yes, thank you. We always have x minus a number. Minus -2 will give me +2. Okay, that means -2 is a center. Then we can, based on our calculation, we can double check if this is really a center, or maybe we make some mistakes. Yeah, you can check this. Okay. That means, again, 11.8, just the summary of 11.8 is the interval of convergence and the radius of convergence. Okay, that means now what we can do. We can try to use the power series, okay, and represent a function based on the power series, as a power series. Because power series, like, even if sounds like complicated because we have infinitely many terms, but actually it's still a power function. It's like x to the power of 1, 2, 3, 4, 5. Like, theoretically, polynomials are the easiest function. Nice and continuous function, and we don't have any roots expression and like rational expression. Okay, that's what we can do. We will try to rewrite different types of function, okay, in terms of the power series. Okay, that means I want to take almost any function and rewrite as a power series. C sub n x minus a to the power of n. Of course, we do have a few tools. Yeah, we have to make some connection, but, and even if you think this seems to be like sounds complicated, because why like we will bother and rewrite a function as a power function? But just what I said, we may have different functions. We may have like e to the x, and we want power series. Maybe sine of x, right? Or maybe just like simple rational function. Okay, that's we want this, because again, these are different types of function. Even if this looks like a not summation and everything, but it's still a power function, just x to the power of n. That means, like, in order to solve some differential equations or some other applications, this is really helpful. Okay, let's see what we can do. We can do this. Okay, that we can represent a certain type of function as a sum of the power series. And we will have a few things. One of the tools that I would like to show you will be using a geometric series. We have to like manipulate and rewrite, but we will use this one. Another way, that means this is one tool. Another way is to take this geometric one, but differentiate or integrate. Okay, that means this will be like another tool. I can show you. And of course, yeah, I typed this question: why would we ever want to express a known function as a sum of infinitely many terms? Okay, but that's what I said. Sometimes it's much easier to deal with the polynomial rather than different type of functions. Okay, that's mean we can solving, that's what I just said, solving some differential equations, approximating a function by polynomials, because we like the polynomials. And it's just, yeah, it's just, ironically, it's this nice and helpful tool to have a power series representation for the function. Okay, let's see. We will start with this. And you remember, power series x to the power of n. If I will expand this looks like that, and we know that this is the geometric power series, and this only works, this is only convergent if x is between -1 and 1. Actually, I should use an interval of convergence notation. And do you remember what was the sum? How can we compute the sum of the geometric series? If the common ratio, of course, the common ratio is between -1 and 1. And what was the formula for the sum? Yes, was the first term, thank you, 1 minus r. That means I can do the same thing. My first term is 1 and 1 minus x, because x is the common ratio. Good? Okay. And of course this. That means now, what is the thing? The thing is that I have my first function. Let me write this way. Having a function, 1 minus x. Yeah, this is just a rational function. What is the power series representation for this function? Is simply the power series x to the power of n. Okay? Of course, only if x is between -1 and 1. I can like repeat for the first time. Okay, that's mean now we can see we do have a first function. Power series representation for 1 over 1 minus x is just x to the power of n. And we can see this is that x, and this goes here. This quantity is taken to the power of n. And of course, I can use this formula only if x is between -1 and 1. Okay, that's me. Let's use this as a tool. Now, what I will have a similar functions to my, let me come back. to this one, 1 over 1 minus x, I will have similar rational function, and I will try to rewrite them and fit to this formula. That's me. Let's see. Express the following function as a sum of the power series and find an interval of convergence. Okay, which means the domain of the function. Okay, that means this function looks almost the same. Oh, okay, I have the solution on the other side. That's what I have. I see one here. The only thing is addition. And I remember that I want 1 minus a common ratio, which in this case, I will rewrite like that. Okay, that's mean now we can see I really fit to my geometric power series. Now I can rewrite this as a power series, and I need the common ratio to the power of n, and the common ratio is negative x squared. And we can see this quantity is simply here, because one more time I will move here. Let's look at this. I can use different color. That's my tool. Okay, 1 over 1 minus x, and then I'm just using, if this is x, this must be x to the power of n. Okay, I have negative x squared to the power of n. Okay, that's almost done. The only thing is we will rewrite a little bit. Because what I will do, I will split everything. In my parentheses, I have negative 1 to the power of n, and I have x squared to the power of n, which will be x to the power of 2n. Okay, now looks a little bit nicer. Okay, I just split these two quantities. That means this is the power series representation for this rational function. But one more thing, interval of convergence, this only works if this quantity is between negative 1 and 1. I can actually ignore I can just simply say between 1 and negative 1. Okay? But let's maybe x squared, it's always, doesn't matter, it's always like positive. That means I can keep this, which means actually is the same interval of convergence. Because I just need numbers less than negative 1. I mean greater than negative 1 and less than 1. That means an interval of convergence is exactly the same. Okay? Because that's the same thing. But we can see I always start with this quantity. This quantity must be less than 1. That's the absolute value of it. That's based on the geometric property. Okay, that's me. Now let's look at the other example. Okay, I have the solution. Okay, let's try this one. Find the power series representation for the function 1 over 2 plus x. Again, yes, I want you to recognize that this is good for my so far first tool. That means what I have. I will rewrite this. I like 1. I don't really like 2. That means I will factor out 2, and I will have 1 plus x over 2. Let me put 1/2. 1 over 1. And again, we don't like addition because we have subtraction of the common ratio. Okay, now looks good. Ready, 1/2. And I have my power series, and is quantity to the power of n. And what quantity? Oh, hang on. What quantity? I have to copy this quantity, negative x over 2. Okay, that's my power series representation. Let's rewrite a little bit, 1/2. And now what I have negative 1 to the n, I have x to the n, and I have 2 to the n. Okay, that's also important step. Oh, my headphones. We will do one more thing. We shouldn't really keep numbers in front of the sigma. I have to put this back. That means I will put 1/2 here. Okay, and we can see nicely that I have 2 to the power of n and 2 to the power of 1. I will combine this. That means my final formula is negative 1 to the n, x to the power of n, 2 to the power of n plus 1. Looks really nice. This is the power series representation for the given function. Let's find, I didn't type this, but let's find an interval of convergence. That means I am taking the same thing, the final common ratio, negative x over 2 must be less than 1. Okay? Again, based on the geometric property. We can ignore negative because absolute value is given in positive. I can multiply by 2, both sides, excuse me, and then we can see we have a number actually between negative 2 and positive 2. That's my interval of convergence, a little bit different because we're dividing by 2. We still want 1. Okay, we do have an interval of convergence. We do have a power series representation. Okay, really nice. Okay, let's see what else. Okay, I have one more because what I have, I will solve this one, okay? And I still have 2 different methods, but what I will do, because I don't want to keep the session too long, I will make a recording for these 2 different methods, 2 different ways how can we get the power series representation, and you can check the recording like tomorrow, okay? But let's do this one. Let's solve this one and let's make sure that we understand this. Okay, that means find the power series representation for this function. Again, this function looks really good. It's the rational function and I have 3 different terms. That's what you can do. You can even, if you will watch this again, maybe you can pause the video and try to maybe do the steps on your own. Okay, that's what I have. I have x cubed on the top. Oh, actually, this looks like, do you see, looks like this? X cubed times 1 over x2 plus x. And we just did this function. Okay, actually, let's use this information. That means I will have x cubed and my power series representation for 1 over 2 plus x, that's this. 1 over 2 plus x is this formula. Negative 1 to the n, x to the n, 2 to the n plus 1. I will copy this. Negative 1 to the n, x to the n, 2 to the n plus 1. Okay, that's also helpful. Okay. Oh, that's the formula. But the only thing is the same what we did with 1/2. We can't keep a quantities in front of the sigma. I will put back there, and then what's happened? This power, sigma from 0 to infinity, negative 1 to the n, 2 to the n plus 1, and then x, this will be x cubed, to the power of n plus 3, because we have n and 3. Okay, that means that's the power series representation. And an interval of notation is the same like in the previous example, -1, from -2 to +2. Okay, that's, we know one way to get the power series representation. Okay, let's see. Okay, that's me. Now I have, okay, maybe I can, do you think we can keep working for maybe another 10 minutes? Or you just tired? I just don't want to keep you, but I can, okay. I know that maybe not everybody is here. Okay, I like the answer. I can do the 10 minutes. Okay, that's me. Let's keep short, okay? And you can shout on the chat box that it's 10 minutes is, we just passed the 10 minutes. Okay, because what I will, yes, I will show you. That's me. I show you the geometric one, but what we did, we just directly used the geometric one. Now, as per first slide for this section, you notice that we have to know how to differentiate and integrate, because maybe the derivatives or the integrals, like will help me to like rewrite an expression. Okay, but then I will, yes, this will be, I can just show you how to differentiate and integrate the power series. Okay, okay, but first of all, let me just remind you this. If we have function x to the power of n, what's the derivative of x to the power of n? Do you remember? Like, what's the derivative of x squared, x cubed, x to the power of 5, 6? N, x, n minus 1. Do you remember this? It's just simply the derivative. Now, that means we kind of gonna do the same thing. Or I can even say this. What's the derivative of this function? Just simply the same thing, but I will keep x minus a, because the derivative of the inner function is. Okay. Now, what is the integral of the power function? Do you remember x to the power of n? Do you remember an integral? Like x to the power of 2, 3, 4, 5? N plus 1, n plus 1. Of course, plus the constant. Okay, and the same thing if we will have x minus a. This one we can think the u substitution, but it's just the same thing. N plus 1 over n plus 1. Okay. That means actually I'm not going to show you something like nothing different. It's simply the same formulas. Okay, that means let's see what we will do. We will differentiate. Okay, I can show you. Too fast. Okay, this is a function with the power series representation. Okay, that's the function. And this is the general formula. We remember C sub n is just the coefficient, constant. C sub 0, C sub 1, C sub 2, 3, 4. And x to the power of x minus a, of course. X minus a to the power of 0, 1, 2, and so on. Okay, that means now let's see how we can, first of all, differentiate. Constant, derivative of constant 0. Derivative of constant, like derivative of x, like 2x, 3x, 5x, is just 2, 3, 5, just that constant. And then derivative of x to the power of 2 is 2x. And I copy all of the constant. X to the power of 3, 3x squared. And then again, 4x cubed and so on. Right? As we can see. This one, I think you will like this because it's simply n and n minus 1. That's what I just did on the previous slide. Because what is important, looking at the sigma notation, in order to differentiate, you will copy C sub n because C sub n is constant. Just copy constant and differentiate x minus a to the power of n, which is n, x minus a to the power of n minus 1. Done. Okay, and that's the expanded. And the same thing for the integral. That's the expanded form, but let's look at the compact form, the sigma notation. Okay? Integral of x minus a to the power of n is simply x minus a to the power of n plus 1 over n plus 1. And copy C sub n. Okay, just simply copy C sub n, whatever it is. Right? And this is like term by term. We can see x to the power of 3 over 3, x to the power of 2 over 2. That means this will be important because we have to know how to differentiate or integrate in order to do the next things. But let me just come back. Please just note, it's simply the formulas that we know. Okay? Okay, I think I still have a few minutes because you gave me 10 minutes. Yeah, this is just, you can check this later. I just want to, okay, like let's see this function. We saw this function in section 11.8 today because we were looking for the interval of convergence, and I think was all of the numbers. Now, let's try, this is J, let's try to differentiate. Okay, that means how can I find the derivative of this? Let me do this. Right? I will, because what you have to do, you have to copy everything what is constant, -1 to the n. 2 to the 2n plus 1, n factorial squared. And the only thing that you have to differentiate is the x, because the rest of them is a constant. Okay, x to the power of 2n. What is the derivative? 2n x to the power of 2n minus 1. Done. Okay, that we can see that's the reason that it's quite easy to deal with this. Copy everything and just differentiate. Okay, I think I have 1 more minute. Let's try to integrate this function. Okay, that's what we will do. An integral, the same thing. Let's copy everything, which is constant, 2 to the n, like whatever is the formula, and just integrate this part. Integral of x to the power of 2n is x to the power of 2n plus 1 over 2n plus 1, which actually I can put in the denominator. X to the 2n plus 1 times 2n plus, over 2n plus 1. Because then we don't have, we can see that's the integral, or plus the constant of integration. And that we can see, that's what I want.